Welcome to Study Loop.
Okay, this is chapter 11, section problem 62, and this is a long one. It's kind of a tricky one, it's a difficult one. Good luck. So the example to go by, this is really similar kind of in around or example number 11.5 in the book. So if this isn't quite enough, go there. Anyway, the question is, this table displays the vapor pressure of nitrogen at several different temperatures, and I've included those here on the left. Use the data to determine the heat of vaporization and the normal boiling point of nitrogen. So, okay, what we need here, as with a lot of these equations in this chapter, is the uh, Clausian-Clapeyron equation, which one form of which I've shown here. So that's like the natural log of the pressure is going to be equal to the minus delta H of vaporization over R times 1 over T2 minus 1 over T1. This is like the general equation that we see a lot here. And what we can do is plot this. And again, whenever you're talking about graphs, if you say blank versus blank, it's Y versus X. So if we plot the natural log of the pressures they give us versus 1 over T, the slope of that graph that you'll make is equal to minus delta H vap over R. And we can kind of see that and understand that, stand that by kind of looking at this equation saying, y is equal to mx plus b. And what we don't have here in this equation is the T1, and we don't have the delta H vap. But we can use that slope again of this graph that we'll kind of make by plotting this data to be able to calculate an HVAP of 5920 joules per mole. Again, take the slope that that gives you, which is 712 if you plot this in Excel, and the negative of that slope times R, which is 8.314 joules per mole per Kelvin, right? Or yeah, is going to be equal to 5920. Okay, the second half of the question, it took me a couple times to get this, but the final answer is 77.5 Kelvin. And the way that we get there is, again, by plugging into this equation right here. So the natural log of P2 over P1 is going to be equal to, the minus H delta vap. And this value now we have divided again by 8.314. And for this one, I chose to, use for the P2 and the T2 data from this chart. And the kind of the trick here is that when you're solving for T1, right, we're looking for the boiling point. So the temperature at which it goes from a liquid to a gas. That's going to be T1, and P1 is 760 torr, right? If that's standard pressure. So that's kind of the trick here, is that you need to be able to put into P1 760 under the 1718 for P2, plug in this number that we just got, and again T2 I've chosen to have it be 85, and then we can solve for T1. Okay, I kind of solved here. If we take the natural log of 1718 over 760, that's going to give us negative 1.15 times 10 to the minus 3. And, well, that's after it had been divided by minus 5919 divided by 8.314. So when you solve this first math equation, that's going to be equal to 1 over 85 minus 1 over T1. Flip that, rearrange it, and here you go. There's a lot of different ways that they can ask you to manipulate this Clausius-Clapeyron equation, and kind of what you need to do always is look at your data and say, okay, what's P2, what's P1, what's T2, what's T1, and once you kind of figure those things out, it's a little bit easier to rearrange this equation and solve for what you need. We could have rearranged this to solve for P1 or T1 or anything else. But anyway, you gotta know how to use Excel for this. So good luck.